purpose of this third video on a possible introduction to a theory of everything is to go over the dimensions of energy in space and in other dimensions of the universe, so that we can show how there can be an energy field that can be associated with the cause of gravity and possibly other forces. The dimensions are separations between bodies of mass or matter, and the best known of these, of course, is space, which is associated with potential energy, which is well known. When you have two bodies separated by space, there is potential energy between them, and for any given pair of bodies, a certain length of space represents a certain potential energy. It's not linear, but nonetheless, it determines what the potential energy is. Now, we can also add a dimension that represents kinetic energy, which means that this body, if this body is motionless, if this were the Earth and this were a spacecraft or a moon or even just something as small as this, if that were there in space, then it is, if it's moving, as it is when I release it, it's a separate body. It's not a separate body until I release it. When it's a separate body, then it has its own relationship with the Earth, and it is separated by another dimension that represents kinetic energy. I'm going to call that the X dimension. Now, we've met this before in relation to the special theory of relativity, where there is a time difference, and indeed part of that kinetic energy is associated with a time dilution. Now, the total energy then, or total separation, is this length here, which is the longest side of the right angle triangle. I referred to it as an isosceles triangle in the first videos, I'm sure somebody noticed. Of course, it's only an isosceles triangle if these two sides are equal. But it's a right angle triangle. And so this represents kinetic energy, and so this represents the total energy. So that if you have, now this body is not really here, it's here in space, but it's here in the dimension that represents the combination of time and what I call the X dimension, which represents in the same scale as space, so that it's what I call the energy equivalent length. And this separation, if it were space, would be potential energy, but it's not, and so it's kinetic energy. But the two are very similar. And kinetic energy and potential energy add together as vectors, because they're associated with forces and energy. And this then is the separation between the two bodies in all dimensions. And these lines of force are multiplied according to the amount of mass. So the equation for this is that the total energy, which is proportional to the product of the two masses of the two bodies, which gives you the thickness, if you like, of the cross-sectional area of the lines of force, and this multiplied by this distance, which I call R0 squared. This is R0. This I call X, and this I call this R0 down here, the longest side. This is R for space, and you can put an N there to represent the different dimensions of space. This is equal to this plus this. So you've got equation here which shows the constant total energy of Rn, which is the 3 dimensions of space squared, plus the value of this, which is associated with the velocity. And I'm going to, the equation is more complicated than this, and there are several equations, but I'll put down the simple form of this, which is m v squared, the velocity, times a time, to make it into a, I usually use the tau for that, the Greek symbol. That squared is the period of the system. And so this is dimensionally now correct. If you were to divide both sides by the time, you would get a V here instead of an R, and this would make this look much more like our definition of energy that we use today. So that's the way in which, now this actually forms in that space a gradient of energy, which is the energy field. It's rather interesting that the energy increases as the square of the distance, not the inverse square law, as Newton said, because he was not comparing a two-body system with different distances. He was comparing several two-body systems representing planets or moons, and they have different energies. So you're comparing their different circular orbits, and there is an inverse square law, because of the centrifugal force is proportional, inversely proportional to the square of the radius. But when you're talking about a single a pair of bodies with a constant total energy, then the energy increases as the square of the distance, and the force increases as the distance, which, let me talk about the importance of the two masses. In Newton's equation for force, you have the two masses multiplied by the universal gravity constant divided by the square of the distance. Now, potential energy involves both masses, which I believe is correct. Both masses affect the energy, and it makes sense, because that tells you the number of lines of force between the two bodies, and both the kinetic and potential energy should have the same dimensions. Well, they do, but then that's done by the use of the universal gravity constant, which has dimensions. And this is the same as saying that, if you expand this, you get that is proportional to the cube of the distance divided by the mass of the central body times the period of the system. So this mass here, which in the case of the moon and the earth represents the earth, in the case of the any planet, this represents the mass of the sun, and those cancel out, which gives you a dimension of one mass. And energy does have dimensions of a single mass, as kinetic energy showed you, but in both Einstein and in Newton's equations. But both masses affect it, and yet the dimensions are only one. And the reason for that is that the period of any kind of trajectory, not just orbits, but any trajectory, even a vertical trajectory, has a period. And that period is inversely proportional to the mass of the central body. So if I drop this, the speed with which it drops, which gives you the period, which is distance divided by speed, that period is inversely proportional to the mass. So the mass of the central body, the Earth in the case of the moon, all this, does affect, its value affects the energy, but the dimension's not there, which is rather interesting. And so this does have two masses in it in terms of its value. But this means that kinetic energy has a value that varies with the mass of the central central body, but it's not included in the equation. So that a body that has a constant period, which this does when it falls, the velocity it depends upon the mass of the Earth, but the mass of the Earth is not in there directly, it's in there through the period. And this is rather interesting. Everything works out all right in the end. There is a single mass in the dimensions of energy, but two masses affect its value. And there's one further thing I'd like to say about the X dimension, because it's rather unusual thing to have to say. If you take the three dimensions, you've got space here, three types of dimensions I should say, because there are three dimensions of space and three of the X dimension and three of time. If you take the, we'll leave time out of it because although it's very important, it's not part of this particular problem or question. If you've got the distance between bodies in space is a real quantity that exists physically, it's a real fundamental variable, it's separation in space, and the energy is also a real variable. There really is energy, it has a definite value, and all of these are in quantum amounts, which means that they cannot be an odd amount. You cannot have fractions of quantum. So they are real existing variables, and they are two of the four variables that I mentioned in the very first video. But this dimension here, the X dimension, is, nature's very fond of avoiding redundancy. Once you have established you have a right angle triangle, and there's no question about that, these dimensions are independent of one another and therefore at right angles. This has a definite length and this has a definite length. This length is constant for the whole system as long as it's life. The Moon and Earth have had an energy that's been constant since the since the Moon was created. Space varies. The Moon, as space has changed as it left the Earth, it had to adjust the diameter of the Earth, or radius of the Earth, as a separation as it went up, so it got more separation, and now its separation is fairly constant. So space varies, and this varies too. But this is not a physically existing variable. Once you've got two sides in that angle, I know that the congruent triangles, two sides and the included angle is the normal qualification, but when it's a right angle, you know that then that's congruent. That is to say, you've established the size and shape of that triangle by having the space and energy. So this here, by default, is there and it has a value. But it's not really there, it's just a make-up space to explain the difference between the full energy and the potential energy. So kinetic energy really is the difference between the full energy and the potential energy, and although we have equations for it, those equations are what we worked out from our theorem of Pythagoras. There really is no such thing as the X dimension, and therefore it does not have to be an integer number of quanta. And as you all know, if this is 3, 4, and 5, or 5, 12, and 13, or any of the many other integer-sided right-angle triangles, this does not have to be true, and this can be any distance. It can be something that is not an integer number of quanta of space, because it's not really a separation. It's just what we know it's there, and it represents, as I said, the speed or velocity squared times the period. So that's a little interesting thing about that dimension, but there'll be more about that later on. Thank you for watching.